I think the public often thinks that I'm spending my days just kind of pointing at a star and going, oh, aliens, on that one, there's definitely, and it's not that. It's all about getting a really large lens effectively. We want just very large mirrors that are extremely carefully done and very stable and very large. It becomes a kind of a crude size problem. And you want to focus that light in and then you can process it. But the really expensive and really difficult bit of the setup is getting that lens, that large lens. And then we also have clouds. So it seems like everyone here has to deal with clouds. And not just clouds, but even in a clear atmosphere, our atmosphere is not visible at all wavelengths, not transparent at all wavelengths. And so often we need to go above the Earth's atmosphere into a space telescope. But now if you want a large mirror, the size of a tennis court, which is kind of what we're aiming for, that's really hard to put in space. So you end up having this problem of having slightly smaller lenses, but in space, or bigger lenses, but on the ground. And the combination of the two is really how we get really good insights into alien atmospheres.
Consistent observations is really important over long periods of time, very frequently. And what you measure is important, but it's more how often you measure it that really comes to light in our work. We've really only for about 10 years been able to do things like grab 1,000 images of the same place and analyze them all together to try to track the way things are changing on the surface. And one of the things that has emerged is that the more frequently you look at places, the more change you find. And that's hard to understand at first because you'd like to think, well, the change is either there or it isn't there. And so if you keep looking more frequently, you shouldn't find more change, but you start finding different kinds of change. So there's kind of consistent seasonal patterns that you'll notice. But if you look very carefully at the seasonal patterns, they shift from year to year. And so if you look real frequently, you start to notice the variability from one year to the next year. You start to notice the variability in the climate. So you'll start to see the effect of droughts. You'll start to see the effect of particularly rainy years. You'll start to see whole new different kinds of variability rather than just people cutting down forests or building cities or that kind of thing. And so I've kind of come to this mantra that the more frequently you look, the more change you find. And it was hard to understand and accept at first, but that's one of the things I've learned about the world we live in relative to the way we observe it, if you want to think of it that way.
It's always a fight with the atmosphere of the Earth, and particularly my field, which is trying to look for the sort of molecules that could signal life. As you can imagine, these are molecules we already have in this atmosphere. And so it's very hard to spot them again elsewhere because the light has to now go through us and then them. And so if you try to go further up, it becomes better. And that's why space telescopes are so useful. But we do put telescopes on planes. One of the telescopes that observers in my field use is called SOFIA, and it's on a plane that just the side of the plane opens up, and there's a telescope in there, and you can go on the plane as an observer, as an astronomer, and observe places far away or nearby, like the solar system bodies. And you're on a plane which is not quite as good as space, but is not quite as bad as the Earth. And so you end up getting a small advantage because you have that much less atmosphere to look through. So we do put them on planes sometimes.
As far as the ones on Earth, you'll actually note most of them are on the tops of mountains. Right, that same issue of getting higher and higher into the atmosphere, so you're looking through less of it. Like I said, one of our telescopes is in Chile. It's on a mountain in Chile. Arizona, the difference between Arizona and Cambridge is quite drastic. But we do keep one in Cambridge just because there is the rainy season in Arizona, and there are dozens and dozens of nights where you're just not going to get any images. And thankfully in Cambridge, it's not quite so bad then. It also allows us to keep one at home that we're maintaining. Like I said, it's a 25-year-old instrument. Things have to be kept up and maintained and fixed all the time.
Oiled
and tweaked all the time. And we have an engineer who does all of that regularly. So that allows us to kind of have a rotating system.
Yes, in 2 weeks, I'm going to go up Mauna Kea, possibly the best place to see the night sky in the entire Earth, which is why we've put quite a few telescopes there. And that's exactly that. It's less atmosphere, but it's also very dry atmosphere. So you want to try and get as little water above you as possible. And so you're trying to really undo the damage that the Earth's atmosphere does to your telescopes, though we are mostly very thankful for, the rain and the breathability of the planet. It sometimes, as an astronomer, you wish you could just hold your breath and not have the atmosphere for a sec, so we could take a better picture.
A lot of the decisions that go into that, into making the images that we see as, receivers of NASA data, the final images, are about making it something beautiful and understandable. So a lot of times they'll choose wavelengths, they'll choose to color certain wavelengths in kind of the same RGB that we think about in light that we use, but perhaps they'll be looking at X-ray light. So they'll choose 3 wavelengths of X-ray light and use that same red, green, and blue spectrum to color it, so it's a little more familiar to our eyes. Sometimes you'll make a choice of colorization to highlight a certain area as well, because it's important to the data of that object. You want people to see perhaps a certain star or a certain area of gas, and it's more about conveying the information that is known behind it, even though it's not that color, because we can't see those colors.
Even when we do process the images, there are choices that we make, there are decisions that we make. It's not just a pure, getting closer to the truth process. The different processes that we use to reduce this data, to clean this data, try and obtain these images, sometimes yield different results, and only one of them can be right. And that's a really difficult thing to hold in our field of work, but it's quite difficult for the public to feel comfortable with. For example, I recently worked on some high-profile research looking at the clouds of Venus to try and detect phosphine, which is here. And if we process the data in a certain way, phosphine shows up loud and clear. But if we process the data in a slightly different way, not a wrong way at all, phosphine disappears. And so the question is, phosphine has to either be there or not. So there is a true interpretation of these images. And yet, we don't yet know exactly what is the right way of processing the data. The solution, you might have guessed it, is more photons. So that's what I'm trying to do up on Mauna Kea. But even us, we're trying our best, and even we don't know exactly how to process these images to get the truth out of them. We don't know if we're creating a spurious signal when we're cleaning out noise. We don't know if we clean out the noise and then clean out the signal by mistake. And so a lot goes into these processes. And I think the public often thinks that I'm spending my days just kind of pointing at a star and going, oh, aliens on that one. There's definitely, and it's not that. It's mostly just looking at a lot of squiggles and praying that the squiggles you get rid of are noise and the squiggles you keep are truths. When I was younger and I was starting to figure out how to take effectively simulations of the quantum behavior of molecules, I learned all the theory, I got the supercomputer, I did all the right things, I solved the right equations, and I did it all. And then I had to show that my simulation, theoretical simulation, had to completely matched with true images of the spectrum of this molecule. And it did. And it was only in that moment when it matched that I realized up until that moment, I didn't believe at all that my work was real. It's in the quantum world. I had just clearly decided to be okay with not understanding it, with it not being intuitive. And I just didn't believe. And it was only when I saw it that it matched that I trusted my own work. I trusted that quantum physics is real, and so it was really surprising to figure out that we as a species have got this far, where we can simulate the quantum world and it works.